This series of surface analysis tutorials is brought to you by Tech and Technology UK. You can download BEX from our official website.
So in this second video recording of the application of X-ray computed tomography data to analyze surface roughness, I'm coming back to follow on from the sample that we finished with at the end of the previous presentation. Just to recap, show the slide. This is the image of the object. It's a section of human tooth, shown here measured with the conventional Taikan Technologies optical technique. What we're currently doing is we've got a section of that which is actually only 2 millimeters by 2.5 millimeters shown above. Let's just make that a bit bigger. And this, turn that lighting off and change that to a different color scale here. This sample, as you can see, is relatively smooth in one section and then has some very rough surfaces at the top here. What we're interested in, as mentioned in the previous presentation, is we're interested in the roughness in a region of this that's been where a very weak solution of citric acid has been applied. So what I'm going to show you in this presentation is how we do that. So the first thing we need to be aware of is that we need a three-dimensional roughness calculation of an area. Now just to recap on two-dimensional roughness, if I just go back to the top-down view, so you can see where the line is drawn, the cross-sectional line. Oh, just let me bear with me a second. Let's go to the top-down view. It's recomputing. And just show that, so across this line here, if we look beneath, you have the cross-section that corresponds to that particular line. And as you know from previous presentations, if we go to these tabs on the left where I'm pointing to, if we switch to 2D form, you can see that for a Gaussian filter, in this case of 0.25 millimeters, we can get some roughness calculations. So let's just see those filters. Here's the waviness in blue. The difference between the two waveforms is the roughness, and here's the roughness. You can see there are some edge effects here because of the edge of the sample, but the parameters are given here for P for the raw surface, W for the waviness, and RA for the roughness. So the RA here, RQ, are around about 1 for the whole, for this line is between 1.6 and microns. Okay, so that's only for that particular line. What we're interested in is the effect of the citric acid on the whole area. So it's much more useful to focus on a particular area here and use the three-dimensional form, and that's shown on the tab to the right here. So I'm just going to show you how we do that. So let's turn these off for the two-dimensional one. Let's remove that. Let's go back to our perspective view of the surface. Here it is. Let's put it in that view, and let's remove the cross-sectional line. So you can see here the sample is 2 millimeters across and 2.5 millimeters, so that's the whole area that we resampled in the previous presentation. So the first thing we need to do is remove the form of the surface so that we level this. And of course this is it's a human surface, so it's a random form. So the best way of dealing with that is to use a Gaussian filter. Because it's an area now, rather than using a line, we go to the 3D form, and before we do that, what we're going to do is we're going to click Edit. That's what we used in the previous presentation, where we used Rotate and Resample. What we're going to do now, because fit form, these are conventional forms, what we're going to do is we're going to filter the surface with a Gaussian filter. That's on the other screen, so let me bring that here. And we're going to use a filter length. Because this is 2 by 2.5, we want a smaller filter length. I know from experience that the 80 micron filter here gives a very nice representation. So if we now filter the surface and apply that, so this whole surface is now going to be filtered with this 80 micron Gaussian 3D filter. Click OK. That's going to take a short time to process because the whole of the data set is now being processed. So We'll see what happens in a second. So coming to the what it's processing here, let's just look at this on the left, and you can see it's done. But here you've got the calculations for the three-dimensional surface roughness. We have to do the roughness measurement relative to some definitions, so that can be, the definitions are given here. We've got the zero mean, or we can take the mean value for Z, a plane, a sphere, etc. But in our case, we're going to use the mean Z value. But before we do that, let's have a look at the surface. So let's just rotate that. So this is all one colour, which tells it's being levelled. If we were to adjust the colours here, because there's some features here, this was quite a sharp edge. If we just remove some of these coloration, so we get a bit more detail of the surface, maybe about there, bring the red down at the top, and just so you can see a bit more. And here it is. So now this surface is now effectively being is flat. So if we look at the cross section, you can see the surface is around. The Gaussian filter is effectively acting like a high-pass filter, so it's removing the DC offset, it's removing the shape here. So we've got a surface which is now nominally around 0 in the z-axis. We've got some features on the left-hand side here. We're not interested in that, because what we're interested in is just a small section where the acid has been applied, so the kind of region that I'm pointing the crosshair to currently. So how do we do that? So let's just remove this and have another look. Now, to do this, we have to use the top-down view. So I'm going to use the planar view here, just looking down on top of the surface. And here it is. Let's just zoom in. If we wanted, as you know from previous, we can add contours to this and make the image much more. Let's try that for a second. Oh, you can see here the surface is rough in sections and not so rough in other sections, but let's remove that. Oh, sorry, click the wrong one. Yeah. Now what we're interested in is around this region here. So how do we just get the roughness for that region? Well, we have to go to the feature we've used previously when we were doing wear analysis. We go to this crosshair here, we click that, and what that does, it creates a brush. And the brush dimensions are, we can set the dimensions here. So let's just use 0.2, got a round brush with 0.2 millimeters radius, and that's the brush that's currently on the screen here. So let's just move that around. Here it is. If I just put that over a region, let's just go here, and I'll show you what happens. If I left click, it's removed that region from the surface. Now, actually, what we want is we want the inverse of this surface. So let's remove the brush. So that feature is there. We haven't. The data's been temporarily removed from the surface. It's not been saved, so we can just put it back in if we want to. But actually what we want to do is just click here, and we've done this in our previous presentations, and simply go to invert the selection. If we were to make the section bad, the section would be removed permanently. But all we need to do is invert the selection. So in other words, click that and you'll see what happens straight away. We've removed all of the surface except and we can just put that back in. So it's just clicking here, include all, takes us back to the original image. And now I have to use the brush again. Let me just bear with me. Go back here, put the brush in, invert the selection, and we'll come back to a very small circular section of 0.2 millimeters radius. So take the brush off. So there's our surface. So if we want the roughness of this surface, all we need to do, so the Gaussian filter has been applied, we've leveled the surface, all we need to do is to calculate the SA value or the SQ value relative to the mean value of Z or the zero mean. It could be either of these, but I'm using the mean value of Z. So I apply that, and then we get the S values. So here you can see a whole list of S values. There are other presentations that are going to be following up on some of these values, but here you can see the SA value, which is the amplitude. It's 0.187 microns. That's for the whole of this region, and the corresponding SQ, if you remember, that corresponds to the RMS or the standard deviation of the surface. It's 0.28 of a micron. So here you've got a very quick way of getting the data. And that's it. That's the conclusion of the presentation. So we've taken, just to recap, we've taken X-ray CT data in the 3D STL format. We have, just look at the file name here, we've rotated that data by minus 90 degrees so that the surface we were interested was the upper surface. We then rescaled it by removing the lower section of data to convert the surface from a manifold surface to a conventional surface. So just a single surface, not a continuous surface. We then resampled the data from STL to .ti format. So now we have a single value for Z at a given position. We've applied a Gaussian filter. The Gaussian filter that we just applied was 80 microns, so that's acting like a high pass on the surface, so we left a relatively flat surface. And then we've applied this brush capability to just highlight a region, and in that region we've done a calculation of the three-dimensional roughness. So just to repeat, all of this is freely available to you. You can download the software from the Tycan Technologies website. If you want any further information, you can contact the company. The software is free to use for the first month, and then if you're interested in making a purchase, you can do so. Okay, I hope you've enjoyed that presentation, and thank you.